So in this session, we'll be like looking into time series techniques. In our previous session, we have discussed about the basics of time series. So we have discussed about 4 different types of components of time series, like trend, cyclic, seasonal, and irregular variations. So I've just show you a small example graphs for all the 4 of them here. So you can see trend here, whereas here it is a cycle, and here it's a seasonal variation, and here it's irregular. So it is like kind of a pattern, but it's kind of irregular. Okay. So we also discussed 2 types of forecasting models: additive forecasting model and multiplicative forecasting model, with all the 4 components. So I believe you remember everything. So now we'll be discussing into different time series techniques and what are the accuracy measures used in time series. Okay. So before we get into that, first we have to like understand the seasonality. So seasonality happens in any data, and before you get into time series, you have to de-seasonalize your data. Okay, to do that, you just use a multiplicative model. We have y equal to trend and seasonality. Trend multiplied by seasonality. So to find out the seasonality, to de-seasonalize your data, you just have to divide your y by t. Okay. So this is called as a de-seasonalized data. So we'll be discussing more about how you can forecast data with seasonal variation. That we'll be discussing in our future concepts. So just to give an introduction with the multiplicative forecasting model, I'm just like explaining this for you now. So there is various time series techniques available. So we'll be discussing all the 5 time series techniques in our session. The first one is moving average, second one is exponential smoothing, third one is auto-regression model, or called as AR model, and fourth one is ARMA model, which is a combination of your auto-regression and moving average. And your final one is ARIMA model, auto-regressive integrated moving average models. We have various other models, but we will be discussing only these models in our session. So first, we will be discussing about moving average method. So moving average is one of the very simplest forecasting technique used by statisticians and data scientists all over the world. So this forecasts the future value of the time series data using the average of the past observations or using a weighted average of your past observations. Okay. So this moving average can be divided into 2 different types: simple moving average and weighted moving average. Okay, so when you're providing your data with equal weights, you can call it as a simple moving average. Okay, but you provide unequal weights for your data. For example, you have a set of data, and then you provide when calculating when applying time series techniques, when you give more importance to time series, recent data, you can call that as a weighted average, weighted moving average method. Okay, so we'll just see the formula here. So to understand all these concepts, we will be using a small example data to understand all of the time series components. So this is the same data that I'll be using to explain all the 5 techniques. So this is a data which of a hospital died another day. So there is a demand for this breakfast in this hospital, and sometimes it is kind of like high and sometimes it is low. So they cannot predict what's going to be the demand, and since the revenue of the hospital is 4% of the revenue is from the canteen of that particular hospital. So they're very much focused on reducing the wastage. Okay, so we have a daily data between 1st October 2014 to 23rd January 2015 for 15 days. So we got the demand of food in this hospital canteen for 115 days. According to that, we have to we'll be predicting the data uh, for the rest of the few days. Okay, I'll give small glimpse of data how it looks like. So this is what it looks like. Okay, so for the week of 5th October, the demand is 41. I mean 41 people ate in that particular hospital canteen. Okay, only for breakfast. Okay, so we have like for few weeks. I'm just showing an example so that you can be able to understand this. Okay. Okay. Coming back to simple moving average, the formula for forecasting the time series data by simple moving average is 1 by n summation of yi. Okay, so here we know n is the number of observation and y is your data, the whole data, and t is your time period. Okay, so 1 by n summation of I equal to t minus n plus 1 until t yi. Okay, so this is the formula for simple moving average. So here n past observations are given equal weightage. Okay, so when you multiply weights here, you can call that as a formula for weighted moving average. So you will be assigning weights according to your value of y. Okay, so that is a formula for weighted average. Okay, so here we are just assuming n equal to 7. When n equal to 7, we are substituting it here and then finding out your f value. Okay, your forecasted value. For example, we are considering only 7 records of the only 1 week's record. So when you say 7 days, so we're considering only the past week data to forecast my tomorrow's breakfast demand. So I'm substituting numbers here. So 1 by 7 I equal to t minus 6. I mean summation of yi I equal to t minus 6. Okay, so when you say yi, it's a average of some summation of all the 7 values in the past week. Okay, so this is your forecast looks like. So you see the graph here, so the actual demand graph is in blue color and the forecasted value is in red. Okay. So when you see the graph, so many of you might be thinking, okay, so we are forecasting something, but the number doesn't look accurate. So we are applying some model. So how are we gonna evaluate all these measures, these models? To do that, we will be using the few methods. So it's not only for moving average. So there are many forecasting techniques developed based on different logics, right? So it is very important to know that when you're using a complex mathematical model, it doesn't guarantee that you're going to get accurate forecast. Okay, so I mean, when compared to moving average method, the ARIMA models are going to be a little complex. Okay, but you can't say simple moving average is less accurate. Okay, so over a period of time, even people figured that this moving average is kind of giving you better accuracy when compared to the complex models. So to measure or validate a model, 4 accuracy measures are used in time series. The first one is mean absolute error, MAE. So this mean absolute error is the average absolute error. Okay, this is actually calculated with n observations. Okay, so the formula is MA equal to 1 by n summation of error. So when you say error, error is nothing but your difference between the actual and predicted value. So y minus f. Y is your actual value, f is your forecasted value, right? Or a predicted value. So summation of error divided by n is your mean absolute error. The second one is MAPE, mean absolute percentage error. Okay. So in here, the formula is 1 by n summation of error divided by y. So this is the average of your absolute percentage error. Okay. So when you take average of your absolute percentage error, okay, is one of the popular forecasting accuracy used by the statisticians in time series. Okay. So we know error is equal to y minus f, which or actual value minus predicted value. Next one is the MSE or mean squared error. So we'll be like using most of the times in regression, this MSE and RMSE is being used mostly in regression as well. Okay, so MSE or mean square error is the average of your squared error calculated over your data set. Okay, so when you have a low MSE value, which means you have a better prediction, right? So it is the formula is summation of error square divided by n. So when you say error square, it's nothing but your difference between the predicted value and the actual value, and you square it. Okay, and next one is the proof mean square error. It's nothing but the square root of a mean square error. Okay, so along with RMSE, mean or mean absolute percentage error is widely used for accuracy measures of forecasting. Okay, so this RMSE is a standard deviation of errors or residuals. Okay, so a lot of companies, including Netflix and Facebook and everybody, use this RMSE value in prediction. Okay, so this RMSE value formula is given by square root of 1 by n summation of error the whole square. Okay, so hope you understood this concept. So there are 4 measures of aggregate error. This is used to validate your time series forecasting model. First one is mean absolute error. It is nothing but your average absolute error. Okay, the formula is summation of error divided by n. The second one is mean absolute percentage error. Here you are taking the average of your absolute percentage error. Third one is the mean square error, which is the average of squared error. RMSE is your square root of your mean square error. Okay, you have to really know this before we get into the different techniques of time series. Okay. Okay, so when we calculate the moving average, when we calculate the future values for a continental breakfast demand at the hospital DAD, the moving average, accuracy is 0.1 or 10.68, or mean absolute percentage error, and RMSE is 5.8. Since this is going to be the 2 important accuracy measures for forecasting, we'll be only like discussing about only these 2 for all our examples. Okay. Next, we'll be like discussing about exponential smoothing. So you had a very good idea of moving average and the forecasting measures right now. So we'll be like moving into exponential smoothing. So when you say moving average, so we have very bad disadvantage there, because you are giving equal weight to all the observations. Okay, so though we provide weightage there, we are not sure like how much weightage we have to provide if we're using weighted average method. So to overcome this, people assign differential weights to the past observations in this exponential smoothing method. So one easier way to assign differential weight is achieved by this exponential smoothing techniques. Okay. So like your weighted moving average, here also the weights decline exponentially, but this is based on your differential weights. There you in the weighted average method you assign weights, whereas here the weights are assigned through differential methods. Okay, so largest weight is given to the present observation and less weightage is given to the preceding observations and so on. So here we have a constant called smoothing constant alpha to assign weightage. So the value of the alpha should always like range from 0 to 1. Okay. So there is like many smoothing constants can be like used. So here we'll be just using one smoothing constant. So you can call that as a single exponential smooth. Okay, so formula for exponential smoothing or a single exponential smoothing method is next forecast or ft plus 1 is equal to alpha, your constant into present actual value plus 1 minus alpha into present forecast. So for the first value, you can always take this present actual value is equal to the present forecast. Okay. So you can reframe this formula as ft plus 1 is equal to alpha into yt plus 1 minus alpha into ft. Okay, so where alpha is your smoothing constant and the value should always lies between 0 and 1. Okay, so this is how the formula looks like. I told you that, right? ft plus 1 is equal to alpha into yt plus 1 minus alpha into ft. Okay, for the first observation, you can always have your yt is equal to ft. Okay, so for example, I have a data for the previous week's breakfast demand and I have to predict for today's demand. Okay, so here I'm just using my previous day demand as yt and today is ft plus 1. Okay, so I'm just going to assume 40 people ate in my canteen yesterday. So alpha into 40 plus 1 minus alpha into 40. Okay, here you can just assume f equal to y. Okay, so when you are using many past observations, so in that case you have to use your formula, use this equation. So ft is your forecasted value is equal to find that you have to use alpha into yt minus 1. When you say t, it's assume t is today's date, t minus 1 is yesterday's date, t minus 2 is day before's date. Okay, so alpha into 1 minus alpha yt minus 2 plus alpha into 1 minus alpha squared yt minus t, and it goes on. So based on the time period, so imagine I'm using only the 7 days, the past week's data to predict my today's breakfast demand. So I'll be using until t minus 7. So ft is going to be my today's demand and t minus 1 yt minus 1 is yesterday's actual sale. Yt minus 2 is my day before's actual sale. Okay, so it's nothing but your time period. Okay, this is today's, yesterday's, day before yesterday's, and the day before that. Okay, so we just got this, but how are you gonna define your alpha? We never talked about it so far. So what is this alpha? How we can just give it? So we know it's a constant, but how are we gonna arrive at this number? Okay, So we'll discuss that, but to show you a small example here. So here we're just assuming alpha is equal to 0.8. Okay. So 0.8 into yt plus 1 minus 0.8 into ft. Okay, so here the weightage is like higher for yt, and the weightage is kind of lesser, around 0.2 for ft, right? Okay, so when using exponential method, we got the map accuracy score as 0.09, whereas RMSE value is 5.3. Considering the alpha is equal to 0.8, we assume the alpha is equal to 0.8. So can we just assume this alpha is 0.8? How are we going to obtain this optimal smoothing constant? Okay, so we'll just look into this right now. So when you have a very smooth data, there is no ups and downs. Your data is very smooth without any too much of residuals. You can have a high value of alpha. Okay, whereas if you have a noisy data, you have to have the alpha as very less, because your data becomes less responsive. Okay, so is that means that you can just assume any number between 0 to 1 to alpha? No, you can't do that. To get a right value of this constant, or an optimal smoothing constant, you have to get a minimum RMSE value. Okay, so usually it is very difficult to calculate that manually. So you will be using various tools like R, Python, and SPSS to get this optimal alpha value. Okay, so you will be calculating RMSE values for various alpha scores, and then so when you get a minimum RMSE value, so you can just assign that here and take that as an optimal smoothing constant. Okay. So I think you know the formula for RMSE, right? So the summation of y minus f the whole square divided by n. So it's nothing but the difference between the actual and forecasted value. You're squaring it, and then you're taking summation of all the values in your data observation and divided it by n, and you're taking the square root. So that's your RMSE value formula. And when you get a minimum RMSE value with sum of the alpha, you can say that that is your optimal alpha score. Okay, hope you got it. Okay, so we have been just discussing about single exponential smoothing. Okay, so what if you're gonna have double exponential smoothing? Okay, so it's called as Holt'smethod. One of the major drawback of the single exponential smoothing is that the model does not do well in the presence of a trend. Okay, so when you have a trend in your data, to capture that, you have to really go for this double exponential smoothing method. So you'll be using two equations to forecast your future value. Unlike there, you just had only one value, right, to forecast. Here you will be having a two equations to forecast your value, and then you sum it up. Okay, so you'll be having one equation for level and another equation for trend. Okay, so this double exponential smoothing is otherwise called as Holt'smethod. This is actually used, as I told you before, when there is a trend or a linear trend present in your data. Okay, so here you'll be having two constants there. Unlike your previous method, that two constants are called slope and intercept. Okay, the formula for this method is called Holt equations. It's to calculate the level or a linear trend. We have alpha into yt plus 1 minus alpha into L t minus 1 plus t minus 1. Okay, it's kind of similar to your forecasted value, but you're just summing up your L and T. Okay, so here for the trend, I mean for the slope, okay, the formula is beta plus So beta into LT minus LT minus 1 plus 1 minus beta into T minus 1. Okay, when you sum up these two equations, you get a forecasted value for the next time period. Okay, F equal to L plus T. Okay, so but here when you see, to find out the intercept, you have to depend on trend, and to find out the trend, you have to depend on the intercept. So what do we do right now? Okay, so for the first initial value of L and T, you always take L1 is equal to Y1. So L1 is equal to Y1. Okay, so you don't have to worry about this. You'll just substitute your Y1 values here. And for T, it's nothing but the difference between the two actual values, Y2 minus Y1. T1 is equal to, you can either take the last two values, or you can take, last four values. In that case, you have to take an average of that. Or you can just take any n number of values, and then you just have to take an average by dividing it by n minus 1, the same thing. So when n is equal to 4, you get this formula. Okay, so that's how you get this initial values of L and T. So hope you got a very good understanding of the simple exponential methods and double exponential method. So when you plot your graph, so it's kind of a little accurate, right? So we have plotted a graph for a simple moving average. I showed you an example, but it was not this accurate. But here you can see it's kind of little accurate, right? So for that, the alpha is equal to 0.8 and beta is 0.05. Okay, so this value is obtained for the minimum RMSE score. Okay, so my mean absolute percentage error for double exponential smoothing method is 9.3%, and my RMSE value is 5.5. Okay, so I think we all got a very good understanding of this. Have you?
Yes, ma'am.
Yes, we just discussed what is what are the different techniques of time series, and what is a moving average, and what is exponential smoothing method, double exponential smoothing method, and what are the accuracy measures that you should be using to validate this time series forecasting methods. Okay, so you got any clarifications on this one?